Good afternoon. Welcome to Paraspar-Lecture organized by the Office of Communication, Indian Institute of Science. Today we have a distinguished speaker, Professor Vikram Jayaram, who will speak on a very interesting topic, electricity from heat, the early history of irreversible thermodynamics and birth of thermoelectricity. Before we begin, we'd like to give a brief introduction of the speaker today. Professor Vikram Jayaram received his bachelor's degree in natural sciences from from Cambridge University and his PhD from Stanford University. He pursued postdoctoral research at Lawrence Berkeley Laboratory and University of California at Santa Barbara. Following this, he joined the Indian Institute of Science, where he was chair of the Department of Material Engineering from 2009 to 2015 and Dean of the Division of Mechanical Sciences from 2015 to 2021, where he is currently an honorary professor. His research interests have ranged over ceramics, mechanical behavior, processing, and small-scale mechanical testing. His current program focuses on the use of cantilevers to measure creep in small samples. He teaches courses on fracture at the master's level and one on functional materials at the undergraduate level. Among the many honors that he has received, some are Lifetime Achievement Award, Electron Microscope Society of India in 2020, J.C. Bose Fellowship, Department of Science and Technology, Government of India in 2017, G.D. Birla Gold Medal, Indian Institute of Metals in 2013, to just name a few. We welcome Professor Jayaram to deliver his lecture.
So, thank you. Thank you for showing up on a Monday afternoon. I hope this will be an entertaining talk. The subject is very dry and arcane. I'm afraid there are not too many ways of making thermodynamics interesting. When I gave this talk somewhere else a few months ago, I was afraid of too many physicists being in the audience. But then today I was told it's a popular talk, but I think most people here are students. So what I will do is, there are equations. I can't avoid showing equations, but you're welcome to ignore them. If you know what they are, then I don't have to explain them. If you don't know what they are, just forget it and listen to me. Thermodynamics is one of these fields where people use it. I mean, practically everybody uses it. But the people who really, really understand it are probably a very small minority. And I suspect even they wake up screaming in the middle of the night, wondering whether they really understood something or not, because it's a field where you deduce so much from so little. So you begin to wonder, what on earth have you found and why? I don't know if anyone here reads C.P. Snow anymore. He was a British academic from the early and mid parts of the last century who wrote some books on political life in English universities. They were entertaining novels. But he also gave a talk which became very famous later on the two cultures. And the two cultures being the humanities and the technological cultures, where he bemoaned the fact, this was in 1950, so there's nothing new, it's been going on for some time, bemoaned the fact that they were diverging from each other. And he encouraged the poets and the artists to acquaint themselves with science in the same way that they blamed the scientists and engineers for being illiterate in the humanities. Unfortunately, I think he chose the second law of thermodynamics as something that they should learn in order to become true, global citizens. It didn't go down very well. The arts and the humanities and the musicians, they were still recovering from the Second World War, and the onset of technology, automation, and all the things that were going in a direction opposed to what they stood for. And if anything, biochemistry was also telling them that the emotional responses to music were all just chemical reactions. So it's very demoralizing to be an artist. A bit like what it's like to be an engineer today, because the computer science people are telling you it doesn't matter whether F is MA or M divided by A or M to the power of A. Data science will tell you everything anyway. So let me start. These are the three characters. Actually, the first one is just for fun. The second two are the main players in this game. And this is really a story about heat. By the way, I got into this because I didn't understand it, but I had to teach. So I teach a course on functional materials, which has nothing to do with my research. And there's one lecture out of 40 on thermoelectrics. Fortunately, it's not difficult to disguise to undergraduates the fact that you don't know anything. But it's a little needling when you talk about something which you don't understand. And thermoelectrics was full of things which were incomprehensible. There were reversible changes, there were irreversible changes. It was never clear which was one and which was the other. It needed materials which were very good electrical conductors but very bad thermal conductors. So they could be neither metals nor insulators, ceramics. So I delved, basically I had to go and read about heat. And this is the story, it's a story about heat. So if you think about it, we're just coming to the, well, I think we came to the end of the first industrial revolution, maybe about 75 years ago. Oops, that's a bit too far. It was in the late part of the 17th century that the first industrial revolution began, steam. That's been the story of life, technological life, until maybe about 75 years ago. It's steam or gas turbine. This is basically the conversion of heat to power. That is what has driven all our lives. And this is an example of perhaps the first vehicle which converted heat into motion. This is a French gentleman, I presume he'd be called Papin, who came, I presume you can read this, so I'm not going to read all these things. He came to a rather sticky end when he tried to demonstrate his innovation. And this is still what happens when there's a new innovation and people's livelihoods are threatened. So that was 1705. So the next interesting thing in this is our friend Benjamin Thompson. This is about 70 years later. This was around the time of the American War of Independence from the British. And some of you will know about his work. He's a practicing engineer. There are no laws named after him because I don't think he did the sums carefully enough. But he did it to satisfy himself that he knew what he was doing. And so he was the one who measured the heat that came from, boring holes in cannons. You had to make a hole for the projectile. And the amount of heat that you generated, and by weighing the stuff that came out, he was able to demonstrate that there was no mass loss. And basically, this theory of heat as a fluid, the original theory of the caloric theory of heat, that was more or less debunked following his work. He also made the point that the amount of heat produced was related to the amount of material that you drilled out and the effort that was done with some sort of a machine, maybe horse-drawn or something, which drove the lathe. And so he did make that connection, but you know it more from as Joule's equivalence between heat and work rather than his work. But he was a very interesting character in other respects. In those days, you couldn't do research unless you had your own money. There was no National Science Foundation or SERP. So people who did research, and I think we owe something to those aristocrats whom we are fond of decrying as, useless people. Many of them just use their own money. So to use your own money, you have to have money. So his strategy was to marry a wealthy widow, who was probably in those days old enough to be his mother. And he was a very charming person, both to ladies and men. And so following that, he went into politics. So it was never very clear who he supported. So in that sense, he was the consummate politician. He tried to fight the American troops against the British. He was suspected of being a traitor. He got out by the skin of his teeth before he was charged with treason, came to the British side, and then when the British lost, he went to England and became the advisor to the king there. It didn't take long for him to realize that the king was not particularly competent. And then he pushed off to Bavaria, where astonishingly he became a prime minister. So you could do things like that in those days. A bit difficult these days with visas and things. And that's where Count Rumford was born. He became a count. Now, one of his major achievements there was the elimination of beggars. It was a big problem. There were a lot of beggars in the streets. They created a nuisance. They had to be got rid of. And so his strategy was, it's a twofold strategy of carrot and stick. He threatened them with arrest. That was a stick. The carrot was, you come into this home where we'll give you soup and there'll be a roof over your head. So that way he got them off the streets. but they didn't want to keep them in the home forever. So he told them, well, the soup is not very good, and before you can drink it, you have to say your prayers. But then if you get employed here, then you can leave this place. So that was his way of getting beggars off the street and into gainful employment. Now, the connection with heat is, of course, that he had to devise efficient ways of cooking. Because one of the major costs in running these kitchens was the cost of fuel. So he is actually credited with inventing, I don't know if you can see that, the modern kitchen range, the double boiler, the baking oven, and the pressure cooker, and the drip coffee maker. So a very distinguished engineer, no laws named after him, but I think it was his work that perhaps set the foundation, even though there wasn't so ready communication in those days, foundation for many of the formal things that happened in thermodynamics by the people that you read about. This gentleman was a little off the beaten track. So the next event in this whole sequence is the discovery of the Seebeck effect. That's Johannes Seebeck, Seebeck, if you like. And he made a circuit from two dissimilar materials. So this is the thing. You have two metals, that hideous blue thing and the black line, and that's a temperature T2, which is greater than T1. So if you just short circuit them, he gets a current. And if you instead separate them, and you can measure a voltage. And he measured the he found that it deflected a compass magnet, and he thought this was due to magnetism. So Ørsted at that time corrected him and said, no, this is a current that's flowing. Of course, current produces a magnetic field. These are all being discovered at that time. And so, but he did some very systematic experiments and demonstrated that this coefficient could be done for pairs of metals. Rather like the electrochemical series, that's a thermoelectric series. So if you have A and B, you get something, then B and C, you get something, then you can immediately say between A and C, you will have something. And so that's the Seebeck coefficient, which is that voltage divided by the temperature difference. Now, a little bit later, I think this was 1826, 1835, was our friend Peltier, and this you will know, Peltier just passed a current and found that he cooled one end and heated the other end. So the end that so if T2 is greater than, if both these temperatures are the same, you will of course heat one and cool the other. But if you start with something which is at T2 and this is at T1, the voltage that you generate will drive a current such that this cools and this heats. That's logical. If the side which is hot gets hotter, then of course it will become an infinite perpetual machine. So you have to go on cooling something or heating something to maintain that temperature difference. And the gentleman called Lenz actually used this to freeze water. So he had bismuth and antimony. So Lenz, this is Peltier, he was a watchmaker. So his living was making watches, and he fiddled around with different types of materials and discovered this. So they were able to freeze water at one end. So this is where things stood until we come to Kelvin. Now, Kelvin is an interesting character. I mean, he's there, and there's about no branch of physics where he isn't there. But strangely, he seems to be popular as a villain. So those of you who have seen an earlier version of Around the World in 80 Days will know that the person who took the bet with Phineas Fogg, this is not the book by Jules Verne, this is a Hollywood version, took the bet was actually Kelvin, the president of the Royal Society. And having taken the bet, he then hired some Chinese hoodlums, villains these days are all Chinese, and to prevent him from completing the bet. So this is the actor who plays Kelvin. He's also a villain in a Japanese comic series, the Japanese manga comics. I assume that it's the same Kelvin, because Kelvin is not a very Japanese name. So it's a bit peculiar. But anyway, he was no stranger to controversy. He wasn't so villainous, but he was certainly no stranger to controversy. And the first one, which he got into at the age of 17, was the problem of the age of the Earth. So Fourier had just come up with his analysis of heat conduction. And so the young Kelvin applied it to the age of the Earth, not measuring the temperature in a bar, no garbage like that. It's the age of the Earth. And so the principle is simple. You make some estimates of what the original temperature of the Earth was. You have some upper limits based on the boiling point of rocks and things. And you have some estimates of the thermal conductivities. So you don't know anything precisely, but what was becoming available were the temperature gradients. So this is the temperature as a function of depth. I'm sorry, the other way around. This is depth and this is temperature. This data was now becoming available. So the principle here is rather like cooking turkeys, or cooking anything, roasting in the kitchen, in an oven. You know that you stop before the outside is cooked. Otherwise, you make the outside overcooked, because the heat from the inside will slowly diffuse to the outside. That's what's happening there. The heat is slowly diffusing outside. So it's a non-steady state thermal problem. And he concluded that based on the available knowledge, the age of the Earth would be somewhere between, the average would be around 100 million years. I'm sorry, I'm looking at temperature. Yeah, somewhere around here. Oh, yeah, somewhere around, that's 100 million years. Now at that point, it was a curiosity, but within 40 years, we had the theory of evolution. Not 40 years, probably more like 10, 15 years. And this led to terrible problems. Because the theory of evolution said that your Earth must have been cold enough to support life for at least several 100 million years, probably 1 billion years or more. So this was a problem. This is a major problem at that time. And you must remember that the theory of evolution was not accepted. And so it had to reconcile all these conflicting observations. Of course, the church had its own estimate, but even if you discount the estimate of the church, and Kelvin said is 10 to 100 million years out the outside, there were the geologists. Any geologists in the room? Hope not. And they said the Earth had existed forever. And there's an interesting conversation which is reported between Kelvin and one of the Scottish geologists. I asked Ramsay how long a time he allowed for that geological history. He suggested there would be no limit to it. I said, you don't suppose it has run through 1 billion years? Certainly. 10 billion years? Yes. The sun, it is a finite body. You can tell how many tons it is. Do you think it's been shining for 1 trillion years? So finally comes the answer. I'm as incapable of, understanding you as you are of understanding me, which is another way of saying, let's talk about something else. Of course, Kelvin couldn't resist having the last word, which amounted to saying, if you use your brains, then you'll figure out what I'm talking about. Now, in the popular fiction, in the popular imagination, not fiction, this issue was resolved in the speech that Rutherford made at the Royal Society. And he reports this. He came to give a talk at the Royal Society on radioactivity as a means of heat generation in the Earth. So he says, I came into the room and saw Kelvin in the audience, and I got a little worried because my theories about the age of the Earth were in conflict with his. And to my relief, he fell asleep. But as I came to the important point, he sat up. All these old professors who seem to be sleeping through talks, suddenly when it's a critical moment arrives, they ask a very penetrating question. Well, he cocked a baleful glance at me. Then sudden inspiration came, and I said Kelvin had limited the age of the Earth, provided no new source of heat was discovered. And that is what we are discussing today, namely radioactivity. And behold, the old boy beamed at me. Now, this has been sort of accepted, but it's actually not quite true. It's a very nice story, which is why people like it. But like most nice stories, it's not the full truth. The point is radioactivity generates heat throughout the Earth. The problem was the temperature gradient. It was not the amount of heat. That was number one. And the resolution actually came from what today you would call a postdoc. And because he was a postdoc, he was ignored. He suggested to Kelvin, what if heat is transferred not by thermal conduction, but actual matter transport? That is, you move, because the stuff is very hot, and over geological periods of time, you may actually have viscous flow from the interior to the exterior, which means there's a completely different way of moving heat around. He was ignored by everybody, including Kelvin, and this shows you what happens to this geothermal gradient as a function of the age. If you have a particular gradient and your age is here, if you add this viscous flow, it increases by an order of magnitude. And today we believe the age of the Earth is about 4.5 billion years or so. And this is well within what you see here. And this, of course, is what you call, what do the geologists call it? Core mantle convection. This is all accepted now. But so all these controversies, a Heaviside, whom you will know from the Heaviside layer, I don't know if you're getting all these WhatsApp messages about the the aurora. Everybody's sending those idiotic, well, they're nice pictures, but after the first 100, you get a little bored. Heaviside was the one who discovered the ionosphere, which enables radio communication. He was one of the proponents of this. Not a very strong one, but one of them. And of course, cooking turkeys, I've told you about. So let's come to the point now. Kelvin's point was, and remember, this was probably a few days after the laws of thermodynamics were established. So the equilibrium thermodynamic laws, which you associate with Kelvin, Clausius, and all those people, had established all these quantities, entropy, and, well, they didn't call it entropy then. But he said the following. He said the flow of current can be converted into heat into two ways. The first is purely dissipative. This is the I²R formula, what you call Joule heating. But the other was a reversible conversion of heat into work. And these followed the same laws as a Carnot cycle. And he assumed that these were proportional to first order. First order means they can be both plus and minus. If you square it, then everything becomes plus. So in other words, when heat flows from a hotter to a colder region, it can do work. And you can apply what we now call the second law of thermodynamics to the process, even though this is not a reversible change. So this is not a classical reversible change, which leads to equilibrium. The thermoelectric effect requires that two regions be at a finite difference of temperature. If you take it to the limit, there's no temperature gradient, there's no thermoelectricity. So this is the thought experiment. I've reproduced it from his text. The Cambridge University Library was very kind enough to send me the entire collected, I just wanted one paper, they sent me the entire collected works of Kelvin. So this is the diagram. So you have all these metals, 1, 2, 3, 4, 5, and so on, and different temperatures. So number 1 is between T0 and T1, number 2 is between T1 and T2. And if you have all this, of course, you can balance this voltage. You run a dynamo, and you can generate a voltage which balances these two. So you can either measure the voltage, or if you switch off the applied voltage, you measure a current. So it's like either a short circuit or an open circuit. So F here is the external voltage. A is the thermoelectric part. It's what you produce. So this is just an energy balance. Gamma is the current, by the way. He used gamma as the current, so I'm just using. So this is the I²R. This is the voltage part, and this is the external voltage. So if the heat absorbed per unit current at temperature T is given by this, then this quantity A is just a sum of all these little alphas here. What happens here? So there are two things happening. One is there is a temperature gradient in a metal, and the other is there is a junction between two metals at a fixed temperature. So there are two things. And so if this is the first law, and if you take the second law, then you take the if you take the work done divided by T, that's what we call the entropy today, but this is 10 years before the term entropy was coined. That has to be 0. So you're applying the laws of thermodynamics to an intrinsically irreversible process. We think 10 times before saying such things now, and but he'd invented it, so he could do whatever he wanted. So what are the various contributions to alpha? So the conversion of current to heat at a junction is what you call the Peltier effect. So two materials, same temperature, and the conversion of current to heat in a temperature gradient in a single material, that's what you call the Thomson effect. So this he had to introduce as something that existed. And if you combine these two, you get what we call the Seebeck effect. So if you apply these numbers, this is what, so let me skip all this. The point is, this is what the first and the second laws give you for that long series of metals in a junction. And if you bring it down to 2, then it comes down to this. So these are the famous Kelvin equations. You will still find them in textbooks, but they're true. So this is the rate of change of the Peltier coefficient. This is the sum of the Thomson and the Seebeck, and this and so on. It's worth just sitting back and looking at what we've actually found here. This is perfectly general treatment. So all the coefficients can change with temperature. Thermoelectric heat is assumed to flow only along the wire. You don't lose it from the sides. Joule heating is rendered negligible. See, this is the thing which is always confusing. You have all these irreversible changes and reversible changes. But because Joule heating is proportional to the square of the current, you can always make the current sufficiently small so that Joule heating becomes negligible. that is I squared, becomes small compared to I. That way you get rid of the dissipative part. Kelvin didn't know what electricity was and he didn't care. He went, damn. Energy bands, Fermi level, all 75 years in the future. Even the electron hadn't been discovered. That happened, I think a nephew of his discovered it, distant nephew, discovered it about 25 years later. The conduction of heat from high to low temperature was ignored. See, if you have a temperature gradient, you will get heat flowing anyway. That's ignored. And in real life, you can't do that, but that's a practicality. The Thomson coefficient is, which is, remember, the voltage that you develop when you have a temperature gradient in a single material is like a specific heat of flowing charge, not a specific heat of charge, it's a specific heat of flowing charge. And within a few years, well, maybe about another 50 years or so, this sort of analysis was extended to concentration gradients of electrolytes, and that's by Helmholtz, thermodiffusion by Eastman, and electrolytes in temperature gradients by Wagner. So we'll see a few examples of these. And they're all relevant today. It's a strange thing. They're relevant in your lithium battery. So it's one of these very obscure phenomena which is actually quite important. So if I put this in simple terms, this current density is Ohm's law plus the Seebeck, and the Fourier thing is, that is the heat conduction is Fourier plus the Peltier. So in both cases, you have the simple to understand relationship between a driving force and a flux. So as a driving force in chemical potential, you get a flux of charge. If you get a driving force, if you have a driving force in terms of temperature, you get heat flow. The off-diagonal ones are the curious things, because here there's a temperature gradient which gives you a flux of charge and a chemical potential, a flux of charge which gives you heat. And the question was, why are these two the same? And this goes back to his original assumption that you can apply the second law even for a non-equilibrium process. So I thought I would just spend a little time here talking about driving forces and fluxes. I hope this is not too abstract. I presume everybody knows this Clapeyron equation. You know, that there's a change in free energy because if you change the temperature and pressure. So in terms of ice and water, you know that if ice and water are to be in equilibrium, then the change in temperature and the change in pressure must follow a certain relationship. So typically that's why in this case, since ice is less dense than water, ice floats on water. So you can hit it with a ship, but it won't sink to the bottom. So the whole heat transfer of the ocean is governed by the fact that ice, the cold part, sits on top and doesn't keep disappearing to the bottom. So this is a principle of refrigeration. By the way, anyway, those are the details. There's a company, there's a startup somewhere in the San Francisco Bay Area, which is using this principle for refrigeration. So it takes a shape memory alloy, which can exist in two states. And the phase and the enthalpy of the phase transition is what subtracts heat from one place and adds it somewhere else. And so to make the phase transition happen, you do work. So, and this of course doesn't involve chlorofluorocarbons and other nasty things. So it's being peddled as such. But you can also do more obscure things. And you can prove, for example, that the rate of change of entropy with pressure, don't listen to all this. I mean, it's not worth remembering. The rate of change of entropy with pressure is the same as a thermal expansion coefficient. It's an obscure relationship. It's true. And you don't know anything about any of these quantities, but you can write that equation. Because it has to do with the fact that these are all state functions. It doesn't matter how you reach a particular state. It's the same no matter what route you take. And the same is true for a dielectric constant. So if I have a polarization along X due to an electric field along Y, then the same polarization will happen along Y if I apply the same electric field along X. Now these are all thermodynamic relationships which occur because of the quantities are state functions. They do not apply for transport. So you can't blindly follow this. So now let's look at situations where you have transport. So again, a simple look at forces and fluxes. And it's all elementary, but sometimes I tried explaining this to my daughter, and they asked me, what the hell are you talking about? So why does a bucket of water cool? It's a standard way of keeping water cool in summer. Basically, the gradients in the water vapor activity drive the evaporation. That is what is driving the evaporation. The humidity outside is low. The humidity, well, water has a certain activity, and that difference is what drives the evaporation. It's the gradients in temperature which drive heat conduction. They're two completely different things. So you can make this artificially low by insulating your pot, putting it in a vacuum if you want, but and make this high by providing porosity and so on. So this is understandable from that standpoint. But the question is, can gradients of one quantity drive a flux in something that does not eliminate the original gradient? See, here you're eliminating the original gradient because if you put more water into the vapor, the humidity increases. And so eventually it'll reach equilibrium. So whether this can happen, of course, all the time. So for example, you have a mixture of gases in a temperature gradient, they will separate. And this is one of the early methods attempted to separate U-238 and U-235. It didn't work. But, there were several methods tried. I think the first bomb was actually based on an accelerator-based technology. And then they went to uranium hexafluoride diffusion with centrifuges and so on. But before that, they tried just putting these gases in a temperature gradient. And because they have different molecular weights, they would presumably separate. It wasn't very effective. So this is the thing we're talking about. Now, there are problems with the Kelvin assumptions, but they boil down to the fact that while the assumptions worked and everything worked, it was not clear what was reversible and what was not reversible. There were some things that were deemed to be reversible, but the same thing in a different situation would have to be reversed. So you had to put it in by hand. So this led to conceptual issues. So we now come to the last gentleman in this game. And this is Mr. Lars Onsager, who was a Norwegian. He went to work with Dubai and then came to the US. He came to teach chemistry at Johns Hopkins, and he was sacked. That's because nobody could understand what he was talking about. His faculty colleagues didn't understand what he was talking about. So the first year undergraduates certainly didn't understand. In those days, teaching was the only thing that paid your salary. You didn't have grants. So he was sacked. They don't say sacked. They use a more sophisticated word. And then he went to Brown. Even at Brown, when the depression and the stock market crash and other things happened, they found that they were not able to allow him, they were not able to retain his services. That's the way it was put. So he was let go at Brown, and finally he settled in Yale, and he got his PhD there. And Yale, of course, where Gibbs had just finished. And so maybe they understood people like him. Or maybe the Yale undergraduates were smarter. I don't know. So he got his PhD because the president of Yale said that my faculty must all have PhDs. So Onsager's chemistry, he was in the chemistry department, he called him up and said, Onsager, no, why don't you write something up, we'll get you a PhD. So Onsager wrote his thesis on the solution of Matthew's equation. Kaushal, you will know what Matthew's equation is. It's some obscure thing about the solutions deal with elliptical drums and things like that. Of course, the head of department didn't know what he was talking about, so he didn't know what to do. The head of the mathematics department apparently told the head of the chemistry department, we'll be happy to sponsor him for a PhD in our department, in case you don't understand what he's saying. This is, of course, an insult. So the chemistry head took his thesis and sent it to leading experts around the world, and took his name off. Because by then, Onsager had written his reciprocity, his famous things. He hadn't got his Nobel Prize, but he'd done all that. And so, to make sure the review was unbiased, this was sent out. Now, you know what happens. Every dean faces this. Nobody replies. So, 100 reminders, and there was no email. You had to send it by boat. Eventually, one gentleman, leading physicist in Europe, replies and says, I'm terribly sorry. It took a long time over this. Please excuse me. This is very interesting, most erudite and profound, and I don't pretend to understand much about it, but what I don't really understand is why you sent it to me. You should have sent it to Onsager. So that's how he got his PhD. So, I think this is where this first began. The idea that you can look at entropy flows. And so here's a schematic. I didn't get it from his papers. His papers are not easy to read. There are other people who have digested them. So suppose you have a reservoir at T and another one at a slightly lower temperature, and you put a bar here. So this is a sufficiently big reservoir, so its temperature remains at T, and this is also big, so its temperature remains at T minus dt. Now the bar has a fixed temperature profile. Nothing changes in the bar. Of course, one end is hotter than the other. Now, the change in the entropy of the reservoir is, okay, this is losing heat, so the change in the entropy is JQ by T. JQ is a heat flux. And the increase here is JQ by T minus dt, or delta T. Now, if you subtract those two, you find this is a rate of entropy generation. And the rate of entropy generation, it has to be in the bar. So this is dropping and this is rising, but they're not the same. So the argument was that the bar produces entropy. And the entropy produced is a product of a driving force. So this was interpreted as a driving force, 1 by T, and a flux. So it's very similar to the power dissipated as a current times a voltage. So this is a flux and this is a voltage. So this was the start. Now, of course, if you had this for a temperature difference, you could do the same with a chemical potential difference. So if you had, and you do any number of variables. So if you had some matter which is at two different pressures or chemical potentials, you can write the rate of entropy production in terms of a matter flux and an internal energy or a heat flux. Now, here's where the insight came. What he said was, each of these fluxes is proportional to the driving force, but both driving forces. And, yeah, that's what he said. So you can then write it in a linearized form. So this is what we do because we don't know what else to do. We write them as linear equations. So the heat flux was dependent not only on the temperature driving force, but also the chemical potential. And similarly, the chemical potential driving force, the mass flux, was written not only in terms of the chemical potential, but also in terms of the heat, the temperature gradient, the driving force due to temperature. So it's very important to write them this way, because all the subsequent analysis depends on choosing the right terms for the driving force. And Onsager set out to prove that B is equal to C. So these off-diagonal components were the same. So I'm going to go through this quickly because I think it's indigestible unless you read the paper. But this is an outline of the way he went about it. See, thermodynamic equilibrium is an equilibrium, is a dynamic equilibrium. So it's not a static thing. So molecules are constantly exchanging energy amongst themselves. Configurations keep changing. A given molecule will keep changing its configuration, but the overall distribution remains the same. Number one. The reversibility of molecular velocity suggests that in a configuration going from A to B, the probability going from A to B is the same as going to B to A. So this is what is famously called microscopic reversibility. Even in equilibrium, fluctuations occur. This is the point. This is a key point. That is, there's a probability of going away from the most probable or the mean distribution. And when you do that, of course, it comes back. Now, when you get a fluctuation, you have a temperature gradient in the sample. So his argument was, when there's a fluctuation and you develop a temperature gradient, even though overall it's supposed to be at a fixed temperature, it comes back to zero, the temperature gradient, in exactly the same way as if you imposed an external driving force. You heated one end and cooled the other. So that's really the key point. And so we'll skip all the rest of it. So the way of doing this enabled the proof to be sufficiently general, though initially he applied it to heat transfer. So this is another illustration. So in his paper, he actually describes how the thought process evolved. So here's a sugar. I've never heard of galactose. Maybe some biologists here they have. It exists in three forms, apparently. And you can have a dynamic equilibrium between those three forms. It's like nitrogen, hydrogen, ammonia. There's an equilibrium. And so at equilibrium, these quantities will not change, but they depend on the rate at which A is becoming B or C, and B or C are becoming A. So these are the coefficients, except that they all balance out. Now the key thing here is, when they balance out, you say that these two are equal, and these two are equal, and these two are equal. In other words, KABNB is the same as KBANA. If you didn't make that assumption, chemists make it blindly. If you didn't, then you would have to maintain equilibrium by reactions of this type, that is A going to B, B going to C, and C going to A. And we don't believe that that makes sense, that there's an internal equilibrium between each process. So that's one. So once you establish this for equilibrium situations, you can do it for departures from equilibrium. So slightly away from equilibrium, you can write these equations. They're the same as the ones that you write for diffusion or anything else or heat transfer. There's a flux, there's a coefficient, and there is a driving force. And if you write that, you will again get these off-diagonal components, which we assume are the same. So this was the thought process which led him to believe that all this makes sense and therefore we should go ahead on this basis. So the problem he took in his first paper is a heat conduction in a crystal with six-fold symmetry. So in six-fold symmetry, everything vanishes except these two terms. These terms are the conventional terms. You have a temperature gradient in this direction, you get a heat flow in this direction. The diagonal, off-diagonal terms are a temperature gradient in this direction and heat flow in the orthogonal direction. Now, in the case of six-fold symmetry, if left-handed and right-handed rotations are not equivalent, if they're equivalent, everything becomes zero. So it's not very interesting. But if they're not equivalent, then this has to be the minus of that. L12 has to be minus L21. And so what he set out to prove is, and experimentally it was known, that L12 and L21 were both zero. So this had been done by Voigt, whom some of you will remember from elasticity. That had been done in the 19th century. So that was what he set out to prove. I'll skip this. Basically what he ends up showing is that these fluctuations end up with a term which goes as the square of the fluctuation. In other words, the likelihood that a momentary fluctuation of heat, remember you're dealing with a system at a fixed temperature and you're talking about what happens if there's a fluctuation and that fluctuation dissipates, goes back. That's the same as thermal conduction, except it's not externally imposed, it's an internal rearrangement. So if there's a fluctuation along this direction, what is the probability that it will be followed by a fluctuation in the orthogonal direction? And what he shows is that it's proportional to the square of this quantity, which means L12 and L minus L12 had to be the same. So this is of course the heart of it, and I'm just skipping through this, but I don't think it's very useful to talk about it in detail here. So once you do this, you can do other things. You can look at different types of fluxes. So here's, for example, you have heat flux, current, and mass flux. This is happening in a battery as we speak in your cell phone. You have heat generated because you're using the battery. You have a current, again, same reason. And there's a mass flux. You've got electrolytes moving all over the place. So here, the diagonal coefficients are what we all understand. You know, this is Fourier, this is Ohm, and this is diffusion. It's the off-diagonal components. So this would be thermoelectricity, this would be thermodiffusion, and this would be what Helmholtz discovered by way of electrodiffusion. So I will come to the last few slides. I'll do this quickly. So we've seen thermoelectrics from the standpoint of the Seebeck effect and the Peltier effect, and there are certain constants like the Seebeck coefficient, the Peltier coefficient. How do they relate to what Onsager did? Because the way he described it, the driving forces are different and the coefficients are therefore different. There are all these L's, and the L's are not the same as the alphas. So to do that, and this is from those of you who've read Callan, you will find this treatment there. You have to write the entropy production rate in a sensible way. Once you do that, you now have a flux of charge particles, and a flux of heat. And now you can assume this relationship, that these off-diagonal components are the same, because we proved it. So the question is, what are these quantities L in terms of the Seebeck, Peltier, and thermal conductivity coefficients and electrical conductivity? Well, what we call electrical conductivity is nothing more than the flux of charge divided by the electric field when there are no temperature gradients. So if you go through this analysis for each of these terms, you put the appropriate term 0, and you've got to be careful what you put to 0. Sometimes what you think is 0 is not 0. Then you will be able to show that what you call the electrical conductivity is the Onsager coefficient L11 divided by T times the square of the charge on the electron. What we call thermal conductivity is a little more complicated thing. And the Seebeck coefficient, alpha, is simply L12, L11 divided by T. And likewise with the Peltier effect. The Peltier effect, you just have the same current flowing from A to B, and you simply have a junction here. So the flux of electrons is the same, current is the same, voltage doesn't change. So the only thing that changes is that the internal energy and the heat here are different from the internal energy and the heat. So U minus J, so this quantity internal energy minus heat is the same on both sides. And this is today what we understand as, if there's a difference in the internal energy, that is the Fermi energy in the two materials, then that is manifest as either a heat absorption or a heat emission. And so you can then relate all these to the original equations. So I've just summarized these here. This is the Onsager way for the flux of charge and the flux of heat, and this is the conventional way. And you'll see that there's a difference because the gradients here are in T and here they are in 1 by T. But here you'll find these two terms are exactly the same. So in a sense, perturbations in a linear system close to equilibrium can increase entropy production, but then the fluctuations damp out and the system comes back to a state of minimal entropy production. And this is where things were until people asked, what happens if you have large fluctuations? If you have large fluctuations, then this no longer returns to its original state. And of course, we are all here because we are a large fluctuation. And so they can be stable and even be amplified to new forms of order very far from equilibrium. They'll, of course, eventually disappear. We'll all pop off, but we'll have a good run for our money while we're around. So, if any of you are interested, there's a book. It's written as a popular book, but it's not that easy to read, called From Being to Becoming, which looks at some of these issues. So I'll give you some examples, since I've bored you with enough numbers, math here. There's some examples of Peltier coolers. When I gave this talk last time, I insulted somebody by saying that this thermoelectric was some largely useless effect, which is in terms of physics is fascinating. It has everything. It has engineering, it has chemistry, it has physics. But in terms of practice, it's useless. Then the gentleman was very affronted. So he's right, perfectly, absolutely right. So Peltier coolers are there everywhere. All your CCD cameras, your CMOS cameras, to prevent heating, they have to be cooled. And obviously, economy of space dictates that you don't have elaborate cooling arrangements, especially out in space. This is a cross-section. Again, these are all from the net. I'm sorry, I haven't given you sources. But if you hit thermoelectric, plutonium, and space, you'll get this. So there's a plutonium dioxide core which generates the heat, maintains the temperature difference, and Voyager 4 or 3 or whichever. One of the Voyagers, it's still there. It's still 1 and 2. So it is still operating. That one has, I think, left the solar system, and they're still transmitting information. So that's what you can do with a power source, which, there's no more photovoltaics that you can use when you're so far from the sun. So these are examples of what is in routine use. Of course, everybody and their grandmother are trying to use waste heat to generate power. That is a big thing today. Use vibrations to generate power, waste heat, and so on. But I don't know of too many which are commercial yet. So here's a lithium battery. So in a battery, there's an anode here and a cathode. When you're fully charged, all the lithium is in the anode, and then it goes to the cathode during discharge. Now, I spoke to somebody who does this for a living. He's a mechanical engineer. But he had to find out what the Onsager coefficients was, because somebody said, what about Onsager coefficient? What the hell is that? Because the flow of current now generates heat, not by Ohm's law, but by this reversible process. So when you do your overall thermal balance, you have to deal with this phenomenon. And this is the last example. Metallurgists will like this. This is a jet engine. And a colleague of mine has made a living out of looking at Onsager's coefficients in this situation. In a jet engine, things are at a very high temperature. I think this is probably an example of a commodity which functions under ridiculously adverse conditions. It's a commodity because we all get into a plane and fly. We don't think twice about it. But this blade here is running at about 100 degrees below its melting point. And the gas temperature is 300 degrees above the melting point of the blade. So something like this, to be safe and to be used by millions of people every day, requires a certain level of engineering, which I don't think there is anything else. I mean, rockets are more profound, but one guy goes up and may or may not come back. So that's different. Now, what is the issue here? Your metal has all these goodies, half the periodic table: nickel, aluminum, cobalt, chromium, titanium, rhenium, molybdenum. But it is protected by a very thin layer. It's about as thick as your hair, consisting of platinum, yes, platinum, nickel, aluminum, cobalt, chromium, again, another half of the periodic table. Now, what is it there for? It is there because this is that layer. And this layer, its only purpose is to take that aluminium there, where's the aluminium? Somewhere here, and make alumina. This is like the aluminium in your saucepan. The reason your aluminium in your saucepan doesn't burst into flame is because of the layer of alumina that forms. The manufacturer will also make it, they'll anodize it and give it to you, so you have a nice thick layer. Otherwise, if you take aluminium powder, it spontaneously combusts. It's that alumina which is protecting you, and so you can go to gate 43 and come back to gate 12 at the other end. Now, over a period of time, this material, which is the thickness of your hair, disappears. The aluminium forms alumina, but it also goes into the substrate because the superalloy, the blade, has a different composition. So everything here is changing. So you can see what happens after several thousand hours. The stuff that kept your coating going is now reduced from this thickness to this thickness. So what is critical here is to know the rate at which aluminium diffuses. Now, the rate at which aluminium diffuses does not only depend on the concentration gradient of aluminium. This is the problem. It depends on the concentration gradient of everything else there, of cobalt. And this is an example of the Onsager coefficients. That is, if you have a concentration gradient, it's like flowing. You flow water through a pipe by having high pressure at one end, low pressure at the other end. Water flows. But if suddenly current started flowing, you wonder what the hell is going on. But that's what's happening here. You have a gradient in one thing, and it is driving a flux in something else. So you have to know what your Onsager coefficients are, which tell you how a gradient in one element can drive the flux of something else. So these are some references. I've come to the last part. I think maybe I'll show you one more slide because it has a contemporary relevance. So there's some nice things on Count Rumford. He's a character, so there are lots of things written about him. I only worry whether some of them are apocryphal. When people get too interesting, everybody makes up stories. Then there's Lord Kelvin's collected papers, Callan's Thermodynamics, and this is the original Onsager paper. This is in PhysRev in 1931. This is the Kelvin Perry and the Age of the Earth thing. You've got to hunt a bit to find this, but it tells you some of the real story behind that controversy. And then a few other things. So I'll just leave you with this. This is a paper from Ajay Sood and others in Nature a few years, I think it was last year. So it's commonplace that if you are at equilibrium, you don't do any work. Nothing changes. And the there's a trade-off between how much power you want to extract and the efficiency. The further you go away from equilibrium, the less efficient it is. That is, the more irreversible the process is. So this paper, which I had a brief look at and couldn't digest, basically says there are ways of overcoming this power efficiency trade-off. That is, you don't have to, if you drive the process far from equilibrium and therefore extract more energy per unit time, you don't necessarily have to suffer an efficiency penalty. If so, I think it's a very interesting thing, but I think that's my last slide. I'll leave you with that. Thank you. Thank you for your attention.
So this is like slight amount of overhead transmission in this topic, although I think I understand some of it. So I think the key point I wanted to understand is at a more intuitive or a particle level, what is it that drives? I understood the concept that Onsager's work says that there are cross flows essentially, like multiple. There's where there's a flux in a different quantity than the gradient in a potential that already exists. Could you just give some insight into what are the physical mechanisms that cause?
It is the temperature changes your carrier concentration. So you get a flux of charge. Most of these are semi-metals or semiconductors. So they're either N-type or P-type. So depending on the dominant impurity, the change in temperature increases the number of free carriers. So that is what is driving it there. So something similar happens when you have an electrolytic cell. Let us say you have heat. The heat is generated wherever the reactions are happening. It could be at the electrode. And then there's a temperature gradient inside. Because of temperature, you can, the species that, the diffusion of species is not the same in the presence of a temperature gradient. So, for example, if you have a gas mixture, it's simple with a gas. You have a mixture, let's say, hydrogen and nitrogen, and you put one end at high temperature and the other at low temperature. You will accumulate one gas at one end and the other gas at the other. So there it's a conversion of the temperature difference into kinetic mobility.
Okay.
So,
Just another question, just to verify. You said the Thomson effect, right? The Thomson effect is a mechanism for converting flow of charge into heat without involving I²R, without involving ohmic loss. Is that correct? Okay.
Because it depends on, it can go in both directions.
Okay.
The heat can flow this way or that way. I mean, or to put it another way, the two ends of the wire are two different temperatures. The current can flow either in this direction or that direction, depending on the material and which the temperature is, what the temperature is.
Okay. Thank you.
Any other question?
What are the prospects of here? What are the prospects of this so-called figure of merit of these materials becoming so good that they will be used in everyday application?
Breaking their heads on this. I've never seen any numbers which excite a practicing engineer to put it somewhere. That's the problem. I mean, if you redesign the exhaust of a car, it's too late. The automobile is gone. I mean, that kind of automobile is gone now. People not even wasting their time doing research on IC engines. So I don't see that, maybe in thermal power plants. I think there are different temperature domains. See what? There's waste heat at very low temperature, around room temperature, and there's at 200 degrees, 500 degrees. The materials are all different. Because all of them peak at different temperatures in terms of ZT. And their stability is an issue. Some of them are very exotic, they're nice for labs, but we don't know how long they'll survive. Interdiffusion is an issue. You have to maintain the chemical purity. You have a temperature gradient, it tends to cancel itself out by diffusion taking place. I don't see any signs of large-scale power generation happening on a commercial basis in the near future. But it will be useful for spacecraft.
Yeah, you have to speak here. It's a recording.
So based on his question, are these phonon interactions that are driving your thermal properties into the electrical ones?
No, just carrier concentration changes due to temperature.
Okay.
See, in thermodiffusion, that's a more interesting thing. It is actually, I don't understand it well enough to explain it to somebody. Let me put it that way. But if you have an activated process, the process of descending from the activated state depends on whether you're going this way or that way. And so you can have thermomigration, that is in a temperature. Supposing I have a material which has two elements in it, and I put it in a temperature gradient. One element will accumulate here and the other one will accumulate here. So that is related to the way in which the diffusion process is asymmetric with respect to where you go through an activation barrier and fall into the neighboring site. That's my understanding of it. But if you ask why, in some case, supposing I have two elements, if you ask me to predict which one will accumulate at the hot end and which at the cold end, I don't have a good answer. But they are governed by coefficients which tell you that this is positive and this is negative.
So we have no understanding of the interaction?
No, in thermoelectrics it's understood, because there it's in terms of the carrier concentration, and I don't think there's any problem with the Seebeck effect. If you know the band structure, and people know how to play with the band structure in order to get these properties. The trick is that you need to keep the thermal conductivity down, because the high thermal conductivity destroys the temperature gradient. That means you are going to waste work in trying to maintain the temperature gradient. Your cold end gets hot. If you're trying to take power out of a hot surface, the cold end has to remain cold. This is what you do in any fridge.
Any other question? Yeah.
So these off-diagonal terms that you're talking about, they're generally much smaller than the diagonal terms, is it?
They are generally. Thankfully.
If there is no other question, we will call it a day today. Thank you, Professor Jayaram. It was a very engaging as well as a very entertaining talk, as how all public lectures should be. We have a small token of appreciation. I would request Professor Kaushal Verma, Chair of Office of Communication, to deliver it to you. We request all of you to join for tea at the reception hall. Also, there is a register kept. If you are not from IISc and would like to get added to our mailing list, please leave your email IDs outside. We'll add you. Thank you. Thank you, everyone.